Hi, and welcome to part 2 of our video on integer constructors and numerical bases. So without further ado, let's jump into the code and see how all that works. So integers have two constructors. Integers are classes, right? If we say type of 10, then we get an integer, right? It's an int class. We can actually look at the internal documentation for integers by doing this. By doing help and then just typing in the type that we're interested in, the class. And as you can see, we have two constructors. We have int x equals 0, so by default it will default to 0. So if we do something like a equals int with no value, then when we look at a, it will be equal to 0. Or we can pass in other numbers as well. So for example, we can say int of 10.5, and that will give us 10, right? Even int of 10.99999, that will still be 10. Remember, we're truncating. Now we can pass in other values that are not floats or not integers. We can pass any numerical type. We can do int of true, for example, which is 1, or int of false, which is 0. We can also use other numerical types, for example, fractions. Now we haven't covered fractions yet, but I'll just show you very quickly how to do that, and we'll look at the details of it in an upcoming video. So let's import fractions. So we're going to import the fractions module, and we're going to say a equals fractions dot fraction, and maybe we'll do a fraction 22 over 7. Okay, so if we look at a, it's the fraction 22 over 7, but it obviously has a decimal representation. And we can see what its decimal representation would be with a decimal point. We can convert it to a float, and we can float a, and this is what it is, 3.142857. Now we can, of course, convert it to an integer, and again we will get the truncated version of that number here. So the next constructor we want to look at is the constructor that has the two parameters where we pass in a string. So remember, we can do something like 1, 2, 3, 4, 5. We don't specify a base, so the default base will be 10. So we get 1, 2, 3, 4, 5. Python prints out integers in base 10. But we don't have to stick to base 10. We could, let's say, look at 101 in base 2, and we get 5. Right? 101 base 2 is 5 in base 10. Now we can use other bases as well. We can say maybe FF in base 16. Well, FF in base 16 is 255 in base 10. And again, the uppercase, lowercase of these letters don't matter. They both work the same way. So if we use lowercase ff, we get 255 as well. Now, obviously, Python is using 0 through 9 and A through Z, so we can encode things using up to base 36. But we have to be careful if we use digits that are beyond the base. So what I mean by that, let's take a look at B in base 11. Well, first let's look at A in base 11. Okay, what is A base 11? It's 10 in base 10. But what would it be if we put B? Well, B doesn't exist in base 11, right? Base 11 is going to have 0 through 9 and A, that's it. So if we do that, we'll get a value error. As we mentioned in the slides, we get this value error, invalid literal. So the next thing we want to look at are the different base representations. Now we do have built-in methods, remember the bin, oct, and hex, that we can use. So for example, we can say bin 10. Now 10 is the decimal number, and the binary equivalent of 10 is 1010. Or if we want to use 5, which was the example we used just now, we get it's the binary number 101. Note the prefix 0b. We can also look at octal. We can look at the octal representation for the base 10, number 10, and that's octal 1, 2. And same thing, we have hex. Let's say we take 255, then it tells us it's 0xff. Now, these prefixes are there to tell us that this number here, well, first of all, it's a number, but this number here is in binary. This number here is in octal. This number there is in hex. So we can also use that same notation for literals. So instead of saying a equals int, 101 base 2, we can also say b equals and we don't use quotes here, so no strings, 0, B, 1, 0, 1. And if we look at A, it's 5, and B is 5 as well. Okay? So we can use these literals by, in binary, octal, and hex by using these prefixes, 0B for binary, 0O for octal, and 0X for hexadecimal. Okay, so now let's take a look at our custom base conversion. So the first method we're going to implement is that one that creates those digits. Okay, so we're going to call this def from base, and we'll pass in from base 10, right? We're going to convert from base 10 to some other base, and we'll use n for our number and b for the base that we want to change our representation to. Now we're not going to handle bases that are less than 2. So if b is less than 2, we're going to raise a value error, and we might pass the message base b must be greater than or equal to 2. Okay, so we'll do that. Now if n is less than 0, we're not going to handle negative numbers here. We will handle negative numbers, but later. So if n is less than 0, we're going to raise a value error, number n must be greater than or equal to 0. Okay, so we're not going to allow those two things. Next, we know that if our number is 0, we can just return it. So if n is equal to 0, return. Now remember, we're going to be returning a list of digits. So in this case, we have to create a list that contains 0, not just 0 itself. Now we're going to create our empty list, which is our digits. And we're going to say while n. So now we're just implementing that algorithm we saw. So while n is greater than 0. Now we could say m equals n mod b and n equals n div b. Now it's really important for us to take the mod first, right? Because we have to take the mod of n, and then we have to do n div b, and then the next time around, this n will actually be n div b, and so we'll be doing n div b mod b. Okay, but it's important that we take the modulus first, otherwise we're going to be taking the modulo of that div right away. So that's not what we want to do. So we can do it this way, and then we would do digits dot insert 0, m. We want to insert that modulo inside the digits as the first element, because we're working our way from right to left. So this is one way of doing it. An alternative way might be to do m comma n equals n mod b n div b. That would work as well. Okay, so we're basically using this tuple notation to do that. But there is actually a function in Python called div mod, and the div mod function returns a tuple that contains the div and the mod. So that's exactly what we're going to do. Now the div we are storing in n, the mod we're storing in m, and div mod returns the div mod in that order, okay, of n comma b, right? Because we're doing n div b and n mod b. So this is an equivalent way of doing it as well. So that's the div mod function. It's quite useful. It does both operations at once and returns the results as a tuple that we can then assign to whatever we want. So that's it. Now all we have to do is return digits. And if the base is less than 2. Okay. So that's our function that's going to generate our digits. So let's test it out. Let's look at from base 10. Let's look at the value 10, the decimal base 10 value 10. In base 2, what do we get? We get 1010. That's what we expected. From base 10, let's say we do 255. In base 16, what do we get? If I can type, we get 15, 15, which is, if we're using these encodings, right, with F meaning 15, this would be FF. So this is not the encoding yet. This is just the algorithm to generate the digits in that different base that we're looking at. So the next step then we have to do is to do the encoding. So let's write it. Let's say encode. Now, what are we going to pass to the encode function? Well, we need to pass the digits, right? That list of digits. And then the other thing we need to pass it is the mapping, right? That encoding map. So we'll pass it. We're not going to hard code it inside the method. We'll pass it as a parameter. And we will encode then using that map. So the one thing I want to do is a little bit of error checking. So if the max of the digits is greater than or equal to length of the digit map, right? So if the highest number that we have in digits is greater than or equal to the number of characters we have in that string, in that mapping, then that's not going to work, right? Because remember that mapping is an ordinal mapping. So we're going to map the first character of the string is going to represent 0. The second character in the string is going to represent 1, and so on. So we need to make sure that we have that. Otherwise, we're going to run into problems. So if that's the case, we'll raise an error right here. We'll say this is a value error, and we'll say digit map is not long enough to encode the digits. Okay, something like that. Something that makes sense to our users. Okay, then we need to create our encoding. So remember, we can do it this way. Encoding equals empty string, and then we can say for d in digits, encoding plus equals, we look at the digit map of d, right? And then we'll just return the encoding. So now if we want to encode, remember now we can try that, and now we need to pass in. So let's pass in this result we had here, 15, 15. And the map that we want to use is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. Okay, so that's the mapping that we want to use to encode. So when we run that, we get FF. That looks more like our regular hex numbers. Now remember what I said about this. All this we can actually change into a much simpler expression. So I'll just comment this out. And we can use list comprehensions instead. So we can say encoding equals, and we need to do a join to get into a single string, and then we're going to say digit map d for d in digits. So we can do that and then return the encoding, or if we want, even simpler, we just return that. Okay, so this is probably a better way of coding this, and then when we run the encode, we get the same thing, right? It's supposed to generate the same thing. Okay, so now we have something that, takes our number in base 10 and gives us its base B representation. And then we have a way to encode it in different ways. So now we can actually combine those two if we want to in a different function. So let's do that. And let's call it def rebase from base 10. And we'll do the number and the base. And in this case, we're going to hard code the mapping string inside this method. So we're going to do something very similar to Python. So the digit map, and there's more than one way of generating the string, but I'm just going to do it by hand. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'm going to use uppercase letters, A, B, C, D, E, F, G, A, B, C, D, E, F, G, H, I, J, K, L, M, N. There we go. And that should be an R. Okay. So that's going to be our map, right? Our encoding map. Now, if base is less than 2, okay, we don't handle bases less than 2, but in this case, we also can handle a base that's going to be higher than 36, right? We've got 36 characters in this string, and so we can handle base greater than 36. So we have to make that test. And if that's the case, we're going to raise a value error, and we're going to say invalid base to less than or equal to base less than or equal to 36, something like that, just to indicate what the problem is. Okay, so base must be in that range. Okay, we're also going to handle negative numbers here. Now, the way we're going to handle negative numbers is we're going to look at the sign of the number, see if it's negative. We're going to then keep that sign. We're going to make the number positive, do our regular, base change and our encoding, and then we'll add the minus sign right at the end before we return the string. So we'll add the minus sign as a string character essentially, before we return it. So let's do that. And we're going to use the ternary if, which if you don't know, that's okay, we'll cover it in an upcoming video. We'll say sign equals -1 if number is less than 0, else 1. So this is equivalent to saying if number is less than 0, sign equals -1, else sign equals 1, right? This code here is equivalent to this code right here. So I'm going to keep the first one a little more concise and still very expressive. And the next thing we want to do is we want to change the sign of number to a positive, right? We want to make sure that it's a positive number. Different ways we can do that. We could, use the absolute value from the math library. We could again use an if statement. What I'm going to do is just multiply the number by the sign. If the number was positive, we're going to multiply it by 1, it won't change. If the number was negative, we're going to multiply it by -1, which means that the magnitude of the number won't change, but the sign will change to a positive number. So we're just going to say number times equals sign. Okay? So now we know we have a positive number. Next, now we need to get the digits. So we're going to say digits equals, we called it from base 10. We're going to give it the number that we're interested in and the base. Okay? That's it. And then our encoding is going to be encode the digits using the digit map that we created here inside our function. Okay, we're almost done. We still have to put in the sign, right? So now we're going to use a regular if statement. If sign equals -1, then the encoding is going to be equal to a minus sign concatenated with encoding. Okay, so if there was a negative sign, we'll add it back here, and now we just return encoding. And that's it. We're done with that function. We now have a method that will take a number and give us its representation in a different base. The number is in base 10, hence why I called it rebase from base 10. So we can try that out. Let's say a equals rebase from 10. Let's take 10 and put it in base 2. And then we'll print e. And then just to check, we'll print and we'll take that string representation that we have, that e, but now we'll use the constructor of the int class that also specifies the base, okay, like this. And let's make sure that we get the same things. So there we go. When we rebased from 10, we had 1010. And when we took that string and put it into the int constructor that uses a string with a base, we got 10 back, which was our original number. So if we were to do, 314 here, then we would get this, right? This would be the binary representation of 314 base 10. And if we put that back into the int constructor, we get it back. So it looks like it's working. Now we can try other ones. We could try e equals rebase from 10. Maybe we'll try, 3,451 in base 16. And then we'll print int e, and we'll say the base was 16. Okay? And maybe we should print e as well while we're at it. Okay? So this is the representation of 3,451 in base 16. It is D7b. And if we pump it back into the constructor for int, we get the same value back. So it looks like our code is working. Obviously, in order to really be sure, we would have to write more exhaustive unit tests. Now let's try lastly a negative number. Let's make sure the negative numbers are getting carried through. I'm just going to change it up here and make it a minus 314. And indeed, we get that. We get minus our binary number, and then we get negative that decimal back, right? So that seems to work. And if we do that with our base 16, we get negative D7b, and then we get negative 3451 back. So looks like it's working. All right, thanks for watching, and I'll see you in the next video.